It's not here. So I want to say a couple things that aren't addressed. What I just said there a second ago sort of means you can actually get a bunch of assignment questions right now without learning anything new. But I want to say a couple of things specific, just kind of overall knowledge so that you kind of understand them a little bit better. So this first 1.6 chapter that we're talking about right now, that's exactly what I was just describing. In other words, it's called allowable stress design. As I've been reading my way through this book and making sense of it, the first time I read these statements, I don't understand like what that title refers to, but then after I wade into it, do some of the problems, look at some of the examples, I go, oh, okay, that makes sense. Because you know how much, if you know how much stress is allowable for a certain material, then you could work backwards and figure out how much force is that given the size of the item that it's sitting on. In other words, and I have a problem like this in an assignment, but one of the things I do a lot, there's a pier that you pour concrete on all the time. That's called a sonotube. So it's kind of like a toilet paper roll, and you just pour concrete inside it and rip all the cardboard off, and now you got this piece of concrete there, and it interacts with the ground because concrete does really well touching dirt. And then you kind of put your post on the top of it. And so that represents your footing, and now that can hold up your deck or whatever it's doing. But for instance, concrete is commonly 2,000 PSI concrete. In other words, that's what it comes with out of the factory. You don't need to know this for this class, but concrete is a 3 to 2 to 1 ratio of rocks to sand to cement. So it's like big rocks, small rocks, and then cement is the actual glue, the really light powdery stuff. And you put it in the ratio of 3 to 2 to 1, and that creates 2,000 PSI concrete, but you can mess with it a little bit. You can change that proportion a bit and get it to be a little bit stronger. So obviously, like for a bridge or something you want to last a long time, and you know, if it breaks, people die. This is something like a sidewalk. I don't know if it cracks, who cares? So sidewalks and driveways and stuff are usually 2,000 PSI concrete, but they'll bump it up. Well, does it make sense that's the allowable stress? You better not put more than 2,000 PSI on that, or it's going to break. So that's kind of the sigma number, right? That's kind of the idea in this section. You already know the sigma because you poured the concrete. Well, then let's work backwards and not put too much force on it. Does it make sense that if I put, say, 850 pounds up here, is that going to break that concrete? And the answer is you don't know. You can't say yes or no yet. What if I said 2,850? Is that going to break that concrete? No, you don't know because you don't know how many inches you put on it. Does that make sense? You got to know the size of the post. If you put 2,850 pounds down there, and this was a square post with a dimension of 3 inches in both directions, so it's 3 by 3. Does it make sense? That's 9 square inches. So now you're taking 2,850 pounds divided by 9 square inches, and you get a number way less than 2,000, and so you're okay. Now, if you put that on 1 square inch, then that'd be 2,850 pounds in 1 square inch, and then it would break. So do you see the concept? It's like we're just working a different direction with the same material that we already know. So that's why weight by itself is not enough. And a post is never going to be 1 inch by 1 inch. That's way too small to hold any weight. It's just going to kind of break. But 3 by 3 is a super common post size. So when I divide that by 9, I'm getting 27 divided by 9 would be 300. That's only 300 PSI right there. Well, that's way strong enough. No problem at all, you should say, right? But these are the kind of decisions engineers have to make and stamp because the average person just puts posts on and doesn't understand what they're talking about. So one of the things, the other part of this is, does it make sense that you wouldn't want the answer to this question to be 1,980 PSI? Oh, good, look, it won't break. Like you want there to be a factor of safety. We've been talking about that just kind of randomly, but just so that you kind of have a sense of this, if I write this out, does this make sense to you? There aren't problems in your assignment about this. I don't know if you're reading the section, but this is one of the sections where I found myself thinking, even though there's not problems about this, this is something they should understand. So that's kind of where factor of safety comes in. It's like force of actual failure divided by the force you allow. So for instance, in this example right here, the force of failure is 2,000. And if somebody said, well, let's not go all the way, let's not allow clear up to 2,000, let's only allow up to say 1,500. So there's your force of failure by the manufacturer. It'll hold 2,000 PSI, but we don't want to push it. So we're only going to we're going to put the weight limit of the bridge, if you will, at 1,500. Well, what is that? 4/3, 1.33, something like that. So in a sense, that would be like a 33% kind of increase in the factor of safety. So you don't have problems about that, but that's kind of the idea. A lot of times the two factors of safety that I see all the time, and I mentioned this to you before, but 1.5 is basically typical. And 2 is typical for stuff that is, what's the word for this? Civil. What civil really means is like stuff everybody uses, bridges, things like that. So you always have a 1.5 for a factor of safety. And it may even be double. So if it was double, then you'd only have the limit would be set at 1,000. Does that make sense? So you're always bumping that kind of stuff in. And the other thing though, that I think is just kind of interesting to know, and we've talked about this some, but does it make sense the concrete manufacturer is saying, hey, this is 2,000 PSI concrete. It's not exactly 2,000 PSI, but remember, they've got to overpromise. I say that right? Underpromise and overdeliver. In other words, if you did break that concrete after it was hardened, probably breaks at 2,500, 2,800, 3,300. I mean, if they're going to say 2,000, then they're going to get sued if it isn't, or at least go looking for if somebody else screwed up. You know, our concrete's fine, but they just mixed it wrong. It was too wet. It was whatever, dried too fast. Somebody else's fault. They're going to be ducking for cover. And so I've got pictures of some of that stuff. But actually, when they do a bridge, this is really kind of crazy. But the concrete truck pulls up, and you have a couple hours before it's hard. So depending on the time of year. So, and if it's a bridge, it'll be truck after truck after truck after truck. I mean, they'll just be right behind one after the other, because it's one truck will do like 10 cubic yards, which isn't that much. It's 2 by 2 by 2 yards. 6 feet by 6 feet by 6 feet is 8 cubic yards. And so it's not much when you're pouring a bridge or something really large. So, but they actually have these little test cylinders. They're a foot tall and 6 inches in diameter, and they're made out of plastic. And they basically, the truck pulls up and they fill 3 or 4 of those. I don't know how many, they fill a number of them, 3 or 4 of those up, and then they dump the rest of the concrete into the bridge. And then they write right on them, this is such and such a load, such and such a day. And they can't test it right then because it's wet. So they actually have to let it set up. It takes 30 days for concrete to set up. So then they take it back to the shop and let it set up. And they get, like I said, they get it marked so they know when it came from. And then the next truck pulls up and they do it again. The next truck pulls up and they do it again. So they have hundreds of these test cylinders, and they wait 30 days and then they break them all to make sure that they actually have the PSI, that job spec. And if they don't, the bridge is already hard. It's been 30 days. They got to go jackhammer it all out of there and start over. So it's like not something you can afford to screw up. But that stuff has to get tested. Just saying it's just because it says it on the bag doesn't mean it actually happened. So it's a pretty interesting process.
That's cool you brought that up, because I spent the day at Mark West structural engineering firm, and they just showed me around, and they went back to their testing center, and they had a bunch of concrete cylinders, and they were all labeled. They had sticky notes or whatever written on them. And I was like, what is all this? I just didn't understand. It must have been circles from their different job sites that they're waiting to test. I didn't know. I didn't piece together until you just said that now.
Yeah, it's pretty cool. And the other thing that's cool is we're there. I mean, there's not a lot more you have to know beyond what we're doing right here to actually be able to make money at this, which is, it's the end of a long road. All the math you guys have done, and calculus, and it's rad.
Well, dude, I was just looking. It seems ridiculous. That makes sense.
So, why would you, I want you guys to think about this. Why would you want to have a factor of safety other than it's just common sense? Because remember, that costs money. I mean, if you're saying, I'm going to double how strong this needs to be, someone's got to pay for that. So, why would you do that? Why would you want to double something? Or why would you always want to make it at least 1.5 times as strong? What can go wrong, I guess is what I'm getting at.
Cheaper than the lawsuit doesn't come in your direction.
But like if you calculated to hold 2,000 and you made sure it was never going to be 2,000 and you tested it and it said 2,000, then why have a factor of safety? I mean, like what kinds of errors, like what kinds of things can screw up? Like I got it all built and there it is and it's all great. Like what can go wrong? Yep, you can have unplanned waits on something that you weren't thinking would ever happen. So maybe it's short term or whatever, you can have unplanned waits. Corrosion, stuff sits there over time and it's not what it used to be. The plan says to make this bar 6 feet long, but you're handing a tape measure and a saw to somebody and saying, cut it. Is it actually going to be 6 feet long? Maybe, maybe it'll be a little longer, maybe a little shorter. Like humans are going to make mistakes. Like it's not, the plan might calculate, but are humans going to make it just like the plan said? They're not. So it is costing people money, but obviously you want it not to break and you want there to be room for a little bit of human mistakes and corrosion over time and things of that nature. So, and then the other part of it is just pure variability. Like I said, if they're promising 2,000 PSI concrete, the variability is probably that and higher. But just because the chart says that steel, a certain kind of steel will hold a certain kind of weight, came out of the ground, came from a factory, it was on swing shift, the guys were drunk, whatever. I mean, it's like stuff doesn't always get built the way, and they can't break everything. In the case of concrete, you just take a little teeny piece of it and break it, and you get to use all the rest. But if you have beams, you can't break every beam, or you don't have any beams. So whatever beam you put in the house didn't get broke. You broke the other one, or one that was like 2 shifts ago or whatever. And did the moisture content change? Did the quality of the workmanship, did that matter? That's one of the reasons I had you guys build those trusses, is like we had a design to build, but it's like not that easy to pull that kind of stuff off with, whatever limited supplies you have and so forth. And it's like workmanship is a part of that too. One of your jobs as an engineer sometimes is to actually go inspect stuff before it gets poured. I mentioned one time, for instance, that if you have a footing down here and you got a wall on top of it and the dirt's going to push the wall over, does it make sense? The back of the wall right here is going to lift up. And so the vertical rebar in the wall, they want it toward the back, not just in the wall, and the guys that are out there like tying wire and stuff, they're like, who gives them for, and they just tie wire and don't pay any attention. But because your butt's on the line, part of your job is to, include a fee in it for you to come out and inspect it, because in the end, when it does break, or if it does break, they're going to call you first. And of course, you're going to hope that you can dig into the concrete and realize they didn't do what the plan said. But obviously, it's better for everybody if you actually understand why it needs to be on one side, and the guys on the job are swearing at you and calling you an idiot. And it's like, no, you understand mathematically why it's got to be there, and you understand what factors of safety are in it. And if we get this in the right location, it gets poured, it's actually going to work. And so that's what everybody really wants, right? So anyway, it's just there's a lot of stuff that goes into assembly. And the plant in White City that made those Boise Cascade I-beams, they peeled their own logs right there on the site to make all of the material, but they bought the glue, something called isocyanate glue. I don't know why that stuck in my head, but they buy that glue from another company. But again, it's chemistry. Like, how do you verify that whatever they're doing chemically to make that glue, is it the same all the time? Can I actually count on it? So they're constantly breaking every 20th board of their product, or a couple of them on each shift or whatever, just to kind of see, is the quality staying up? Because they can't, they have their own people that can make mistakes, but they also have products they're bringing in that they're just trusting that company is coming in saying, but in the end, they're the one that's going to get a call if something goes wrong with their product and it doesn't work well, even though people do it in a court of law. And you've done this too. It's like the first time when you screw something up, the first thing you think is like, how can this be someone else's fault? Or like this car accident, you're thinking, oh, how did this person, oh man. So anyway, long story short. So that's an important concept. And then let me just show you one other thing, with just sort of one introductory kind of logical concept. 1.7 is actually talking about load factors. This is kind of interesting too. And this is something I learned from reading your book. Because as I've admitted to you guys, I'm kind of teaching myself this stuff. So I'm just going to write down something that I saw in your book. This is exactly a line that was written from this section. I'm just copying it right now. So these are load factors, and it's exactly what I was just talking about. That 1.33 is like adding 33%. You're adding 33% to the what it can do, or taking 33% away, if you will. Well, notice this is basically plus 20%. You're adding 20% on top of that. What's D? D is the dead load. L is the live load. And S is the snow load. So in the case of a roof of a house, those might be all the different things that cause load to that house. Again, we've talked about this a little bit, but dead load is of course the roofing and the rafters and so forth. Whereas the live load is things that come and go, which could be other loads. Oftentimes that live load is actually snow, but they're things that could come and go on a roof. Tree falls on it, that kind of a thing. But what they point out in the book that I thought was really cool was live dead load is actually really predictable. So you don't need to add that much. 20% over is just fine, even though we said it should be 50 over, like it's almost always 50% over. 20% is fine because it's very predictable what dead loads are going to be on it. You know exactly what materials are there. Whereas live load, is live load that predictable? You kind of don't know what the idiot might put on top of that roof, right? Might put a hot tub up there. It's like, who knows? So they add 60% to that one. And then why would the snow load be so, like that's actually lower? Does it make sense they took it away? If it had been 1, then that's like just leave the snow load alone. But here they're saying, just half of it's fine. And what that's about is just the fact, because live and snow load are kind of related to each other. The idea is, are you going to have a hot tub and a snowstorm simultaneously? That kind of thing. Is it likely? Because this is interesting, is it's probability, and that's why I wanted to bring it up to you guys, because it's kind of probability. Because you can say, I'm sorry, we're just going to have to pour your whole house solid concrete. You may won't be able to go in it, but at least it won't fall down. I mean, in the end, that's what engineers are kind of trying to do, is just make sure stuff doesn't fall down, because they obviously don't want people to die, but don't want to get sued. But it comes down to probability, right? Because I get pissed off constantly with the construction I'm doing, because they're always specking new stuff, man. They want all these clips and tie downs and stuff in the concrete, and it just costs people money and time. And it's like, I get it from a let's not kill people perspective, but it's like we have 500,000 houses around this valley that were not built with these codes, and they still seem to be standing there. So it's like, why do we really need to do this kind of stuff? And if there is an earthquake, you know, you're still not able to guarantee with some of the new things that we're being asked to do that's going to keep the house from sliding off its pad and so forth. So, but it's probability. Do you see what I'm saying? It's like, was this likely to happen? So, you know, this little formula that they put up there, they pointed out in the book, it's like, it's not likely that the maximum live load that's weird, not just 100%, but 160%, because something weird happened, is going to coincide with a huge snowstorm. So we don't need to add a 1.6 snowstorm on top of a 1.6 live load, because it's unlikely that those two things will happen. So I don't, as kind of just a designer, feel the freedom to make those kind of decisions, but the engineers, a lot of times when I call them and we're making some decision about some footing, and I love picking their brain just because I understand enough of what they're doing that I can actually learn stuff from it. And they a lot of times will have a far smaller load on something than I do, because I'm using just kind of a generic load that's always used for roofs. And they're like, oh, in this case, you know, you can actually just use 7 pounds a foot. You know, I don't feel the freedom to do that. But this is kind of where it comes from. So anyway, I want you to understand that.
How strong of an earthquake should houses be able to withstand? Is it that they don't fall over, or they just?
Yeah, I mean, it really has to do with the amplitude of the waves, because in the end, it's kind of like if you had, you know, a piece of plastic on the pool and there was waves in the pool, then the plastic would kind of do this. Well, the crust of the earth will do that too. So it's really about the amplitude of those waves, and how much it's going to shake the house. And so it's kind of, some of it's timing, like the Tacoma Narrows, like the timing of the resonance of the waves allowed it to get bigger than it sort of should have, and that's what caused it to break apart. But it feels very unpredictable to me. I mean, I haven't waded a ton into that, but you're basically just talking about the house getting shaken. And one of the complicated parts of a house is you have concrete in the ground, because concrete doesn't deteriorate with dirt. But then you start with wood. Well, then what's the connection between wood and concrete? Well, there isn't one. Like, you have to put a bolt in the concrete that's tied. It's got a J on the bottom of it, because it's so it won't come out of the concrete. And then you bolt a piece of wood down to the top of it, and then you build the house on that wood. And so that connection is kind of sketchy, because your house can just vibrate right off of the foundation, if you will. Generally speaking, your foundation is buried in the dirt, so it's not going to move with the ground, but your house can kind of vibrate off the foundation if it's not one of the codes they changed recently, which again kind of annoyed me. They have this 1/2 inch bolt that sticks up and you got to have one every 4 feet. Well, you can appreciate that's a calculation some nerd like one of us made. Like, why is it every 4 feet? One out every 3, one out every 6, you know, like what distance is actually necessary there? But these bolts are a 1/2 inch tall or 1/2 inch in diameter. And again, can you picture shear there? Because if the house is like vibrating around, does it make sense they could shear that bolt off? So, you know, where did a 1/2 inch come from? Well, the stuff we're studying right now. But on top of that, we used to put a flat washer that was about 1 inch in diameter. So you drill like a 1/2 inch hole for the bolt to go through, and you put a 1 inch washer on the top of it. Well, they decided, no, that's not going to work because the wood could lift up and just, you know, fold that washer and it could come up. You know, my thought was the house weighs, you know, 50,000 pounds. It's not going to lift up in the air when you have bolts everywhere. So they changed it, and now it's got to be a 3 inch by 3 inch steel square plate. And on my last house I built a few years ago, that code changed when I was picking my nose for 10 years. I didn't build a house, and they came out to inspect it. And it's like, you got to have these big washers. And so the guy was a pretty nice guy. And I just said, dude, how many houses in this valley are built with this? How about instead of me having to replace all those, that you say, you know, lesson learned, I get it. It's not like I'm trying to break the codes. I would have put those on there if I'd have known that. But it's like, I don't want to do this again. I don't want to throw these in the garbage and go buy all these other ones. How about there's 50,000 houses in the valley that are built like this and they're okay. And how about we just sign this bad boy off and we get on with this here, you know?
It's a hard sell right there.
To my surprise, he did. So nice guy.
Not gonna lie, if an earthquake hit, that's pretty violent. My house can't even like handle the trees around it or like messing with the concrete. So like an earthquake, my life would be like
Nowhere.
yeah, my house would just be decimated.
Leveled.
Yeah, I think so too.
Okay, well, let's wade into this. Armed with those two basic equations, what all you're really going to notice here is in the last chapter, we had forces and bars like this, and then they just asked us to find the shear stress that it put on those plates down there that are holding this whole assembly up. Well, in this section, they're telling us what these plates can handle. Notice it says they have an allowable bearing stress for that material of 400 PSI. So it's not like it's not 2000 PSI concrete. It's like some weaker version of that. That's what it can handle. But notice the size of those two different supports. Notice one's bigger than the other. The B one looks bigger than the other one. And so it's like they're not necessarily the same size. You see why that's why 400 PSI is a cool way to say it. But we got to know PSI, but then we also got to know how many square inches that is. So like what size is that that's sitting on there? And so we're kind of working backwards here. We know what stress it can handle. We know that whatever that material is, it can handle 400 PSI. But now we got to put a limiting value on that P. In other words, what's the biggest P that we can stick on that side over there so that it doesn't stress that too much and break it. So the formula is not any different. So anyway, let's just kind of fly into this. And notice they're 2 inches by 2 inches and 4 inches by 4 inches. And so, sweet, let's just kind of fly into this. There's more than one order I could do this in. Like I could even calculate this right now. In other words, we've been saying this, right? This is and notice I'm not talking about shear forces here. Do you see how I'm not using the tau one? Because these forces are straight down on it. So we're talking about a force that's perpendicular to the surface. So I'm only interested in the normal stress, not the shear stress. You understand that? There's no force trying to get this to slide in that direction. It's all straight down on it, normal to the surface. So that's the only formula I need. And so in this section, really what we're just talking about is instead of just calling that sigma, you know, it's kind of like we're thinking of that as the allowable number. And we've been given that. We were told that that's 400. So we know that's 400. And I find myself wanting to stick the units into that all the time. And sometimes even not even writing PSI, but even writing pounds per square inch so that I kind of know the other side. Whatever I do over there, it's got to result in the same units. One section I got into later in the book, like chapter 5 that I've been working on, I was getting all the problems right and I didn't even look at the section. And it was entirely because I just let the units tell me what to do. which is a really powerful tool. So I'll show you that when we get there. But so it's like, okay, cool. I know the answer to that question. Do I know the normal force on it? Well, if this is the normal at A, I don't know what that force is, but I do know that that A is 2 by 2, which is actually 4 square inches, don't I? So that means my kind of maximum normal at A better be 400 times 4. And notice normal of A is going to be pounds then, because it's pounds per square inch. So I end up with 1,600 pounds. Like that's going to be kind of like my max, if you will. I can't exceed that. That's my allowable limit. I can't put more than 1,600 pounds down there. And of course, your book would probably call that 1.6 kips, right? And then for the other one, I also have 400 pounds per square inch. But it's 4 by 4, which is actually 16 square inches. So if I draw a normal of B, and I could call that force of B. There's nothing magic about that. It's just, it's kind of good that the reason your book uses normal is it's important to remember that there's two forces here. Normal is perpendicular to the surface, which is often what you're doing when you're supporting something. You're usually putting it straight on top of it. So you could call this force of A and force of B. It's what we always did before, but normal is the same thing. It just means, it just tells you it's perpendicular to the surface it's landing on. So if I multiply that, I get 6,400 for the normal of B. So I'm kind of storing those away for later. Maybe I need those right now. Maybe I need them later on. But of course, the interesting thing is does it make sense if you just pick the value for P? It's not like it's going to match both of those, because it's really kind of like one could fail and the other one may not fail. That's kind of the issue here. Okay, cool. Well, let's now go do what we've done before, which I think is a very good thing to kind of delineate in your notes. Reactions at A and B. So if I say, okay, cool, what's the sum of the moments around, I don't know, A? What's the sum of the moments around A? Well, let's see, I've got 2 kips right here, but it's aiming right at A, so it's not going to cause any rotation, but that next 2 will, and it's going clockwise, so that'd be negative. So that's 2 kips. And because they're all kips, I think I'm going to leave it alone. Just going to leave it as 2. I'm tempted to write 2,000, but, and it's a distance of 5 feet. And then I've got 3, which is also clockwise. It's a distance of 10 feet. I've got 2, also clockwise, at a distance of 15 feet. And then I've got P down there finally, which is also trying to get it to rotate clockwise. And it's a distance of 15 plus 7.5, 22.5. And then finally, normal of B, which is pushing back. Normal of B is pushing back, and it is also 15 away. And if this is going to stay static, well, then that'll all be equal to 0. So that's kind of cool. So since I did it this way, notice that I have a maximum value for normal of B. It's not saying it is the normal of B, but I have a maximum for this. So if I say, 6,400, I guess I have to say 6.4 since I did everything else in kips, right? So I'm going to kind of leave the word max in there. If I do that, then I can actually solve for P. If I do, I get P is 1.1556. So if I go over that, then that means that 6.4 is going to go over. Notice there's no factor of safety on this. But if that was calculated as a certain factor of safety, Like if this was a 1.2, again, you won't see this in your assignment, but if this was supposed to be a 1.2 factor of safety, then I would take this number right here and multiply it by 1.2 and just make it bigger.
You have to know what's happening at A as well.
That's right. Now, something happens at A too, and maybe that breaks A. Does that make sense? So we can't just say, hey, I'm done. So that's exactly right. So in a sense, what I need to do now is come back and remake this calculation, but do it around B. And I'm not sure off the top of my head, but perhaps we could switch to the sum of the forces in Y here. Does that make sense? Because now I know I kind of have a value for P, and so maybe I could just switch, maybe the sum of forces in Y would make this easier. But I'm going to do it this way anyway. So let's see. Okay, if I do this around B, what do I have? Well, I got that first 2 at the beginning there, trying to get it to go counterclockwise. So that's actually positive. So that'd be 2 times the distance of 15. And then the next 2 would be a distance of 10. And the next 3 would be a distance of 5. And then, of course, this 2 makes no rotation around B because it's right aiming at B. So I don't need that one at all. And then P is trying to get it to go negatively. It's trying to get it to go clockwise, and that's a distance of 7.5. And then lastly, that normal of A is also trying to get it to go clockwise, so it's also negative. So normal of A, and it's a distance of 15 away. And then it's also equal to 0. So if I throw in my value for A, if I throw in my 1.6 kips max for A, then I get a value for P of 5.4667 kips. What do I do with all this? Like, first of all, we didn't get the same answer. That's not good. We got 2 different answers for P. And this is not the only way to do this, but what do I do? Did I make a mistake? Did I? Exactly. You got to pick the weakest one. So, because basically what that means is we won't recalculate this, but when we stuck 1.6 in here for this, we got this for a P value. But what if we went back up here and we took that 5.44 and we put it in for P up here? What would happen? We'd get a number way bigger than 6.4, and then that would break that support. Do you see what I'm saying? So there's more than one way to do this. But if in this case, I just sort of calculated them both ways and then just pick the minimum one. But to the extent that you were trying to get your mind around this, because I don't think this is obvious, you might take the time to go through that P back. And of course you can tell, like when P was 1.15 up here, that put us right at that maximum limit, right? So what's going to happen if you put this large one in up there? Well, it's just going to get way bigger. And then of course it's going to break that. So it's no different. It's the same set of formulas that we worked with before, and there's no new knowledge in finding these reactions at this point. It's just that we're kind of trying to work backwards to put a limit on our bridge, if you will. Well, let's just take a look at some more of these guys. Let me see what time it is. Yeah, let's do this one. So I got this one wrong first when I did it. And I imagine you might make the same mistake I made, but take a look. And they didn't say anything about this in the problem, but notice how this crate is basically hanging here. And over here, it sort of appears that this is like kind of like a roller, like it'll roll that up and sort of cause this bar to kind of tip up and down and so forth. Well, when I first looked at it, because this thing right here is round, I thought I thought this rope just went right over the top of it. Does that make sense? It was like a pulley. But this is actually kind of like a knot is tied right there. This comes over and attaches, and this comes up and attaches. So that, and it kind of makes sense. When this rope pulls, this thing's going to lift up, but this length right here is never going to change. You see what I'm saying? There's nothing to control the length of this line right here. You're just stuck with what it is. So anyway, the boom is supported by a winch cable that has a diameter of 0.25 inches. And again, you shouldn't be surprised when you read all the problems in the rest of this book that they're always going to tell you what size things are, because that's going to make a huge difference. That's part of that pounds per square inch calculation. And it has a normal allowable stress. Notice it doesn't just say sigma, it says sigma allow of 24 KSI, in other words, 24,000 PSI. And then they say, okay, that's what the allowable limit of cable is. And notice I have cable in both places. It's the same cable, which I don't necessarily think is obvious here either. But the cable, I can look up in a book and it tells me what its PSI strength is. And that's what I'm being told. 24,000 PSI is what that cable will hold. And then they're saying, okay, great. Well, don't lift too big of a cart. Lift too big of a load then. So what's the greatest weight of that crate that I can lift? And then they said, if the angle is stuck at 30 degrees. And so is what?
KSI is that 1,000 pounds? Or
yeah, 24 KSI. The K is 1,000. So it's really, it's thousands. So this is actually 24,000 PSI. It should say KPSI. You see what I'm saying? There's a number of things like this that are just weird. Exactly. There's all kinds of stuff. It's like K means other things. Every letter in the alphabet gets used in a class like this. So, and of course, that's something you're going to see a lot, because any real project you work on, I've told you this is never going to be in pounds, because nothing ever lifts pounds. It lifts thousands of pounds. And so they just try to make it simpler. So it's always kips. And anyway, so we know this thing's 30 degrees. Cool. So what do we know? Well, looking at B, and actually I'm going to stay over here a little bit. So in the end, this weight is obviously going to pull down. So if I isolate B as like a joint in the bridge, does it make sense? There's only one member. There's two members here. There's this member and there's this member that are going to kind of defeat that. Does it make sense? This is the only one that can defeat that though, because the other one's horizontal. So that has to push up, which basically means it also pushes this direction, which means that's under compression. And as a consequence of that, this is also pushing right, which means this actually has to pull back left, which it's doing both directions. And so that means that's under tension. So in terms of your free body diagram, just looking at that point right there. So out of laziness, because it's such a fairly decent figure, I'm not going to redraw it this time. But does it make sense? I know what's under tension and what's under compression just from the free body diagram and the fact that there's not too many things hooked to that. So I'm just going to call this, W for weight instead of P for pounds, and it's not really normal to something, so that's why I don't want to call it N. I could call it force of B for box or something, all kinds of names. But notice if that's the case, then kind of in the same order I just realized all of that, I might start and say, okay, well, what are the sum of the forces in the Y direction? And you should see this is directly knowledge that came from your statics class. So I see that I have W going down, and I see that I have the force of BA or AB going up, but what's the modification for that? It's not going up, it's going at an angle, but what part of it is going up? Given that this is 30 degrees. So that's the component, right? Sine, not cosine, sine. So sine of 30 degrees would be its modification. Those are the only two forces, and I need those to be 0 so that that joint's not moving. In order for this to sit here, that's what I need to have happen. So I guess I can say that W equals force of AB times the sine of 30, but I'm not very happy with that because that's got two unknowns, right?
Oh, I know. Never mind that. You're using like-
Yeah, or I could divide by the sine of 30, and then I could say force of AB is W divided by the sine of 30, but I don't like that equation. It's true, but I don't like it because I can't use it. I can't solve for anything. So I'm wondering, do I need something else? Did I not give enough information? Did I make a mistake? You need to learn to think like an algebra student, just like write stuff down. What I like to do, that I've demonstrated a lot, is kind of like highlight this. Basically, in a sense, I could kind of throw away everything I did now, and I just need that, right? So I know that's there. It's not the answer to any questions that I'm interested in, but it's like, there's a truth, there's an algebraic truth. If I happen to run across W someplace later, then I'll be able to find force of AB. If I happen to run across force of AB later, then I'll be able to find W. So cool, sorted that away. Okay, great. Well, now I'm thinking, I don't know what to do, but I know that the sum of the forces in X also have to be 0. So let's see what's going on in X. Well, notice I got that cable going left that I have T written on for tension. I have that thing going left, and I haven't given a name to it yet. Let's see, I'm trying to decide if I should give a name to it. I guess I will. I'll call this point C over here, and I'll say, well, it's going left, so that's negative force of AC. So it's going left. I don't know what that is either. And then I got that AB force going right, so that's plus. So I got that force of AB going right, but the part of it that's right would be the cosine of 30 degrees. And that's it, and those need to be 0. So now I'm kind of in the same spot. I have force of AC equals force of AB cosine of 30, but that doesn't really help. I noticed that both of them have a force of AB in it for whatever that's worth, but I can't really do anything with that either just yet.
Not be force of OBC. You could do your F of Y solve for force of AB, which would
I'm
give
sorry,
you
FBC.
W divided by sin 30.
Let me fix this really quick before I answer your question. Yeah, I meant to say force BC. I'm sorry, from B to C. That was kind of dumb. Okay, what did you say?
Go back to your Y equation and solve for force of AB, which is W divided by sin of 30, and then go to your second equation, plug that in, and then you'll be able to solve for the weight of the box. Because you know the force in the BC, or at least the max force. Yeah, the cable.
Yeah, and I noticed I got the cable in 2 different places. So that's kind of interesting. They appear to be asking me about this cable. Does that make sense? And this problem isn't totally clear. My first thought was it's the same exact cable in both places.
I feel like anytime they give you sine and cosine, they will.
Could be. But Caesar's right in the sense that at least they both have a force AB. But notice algebraically, right now I have 2 equations and 3 unknowns. I can't solve that unless I've got another equation. I got to know something else. So yeah, and you alluded to this, but where does that sigma allowable, that 24,000 PSI come in? Because I'm thinking of this equation. I'm thinking this equation right here. Notice again, it's called normal stress. Are you cool with why it's called normal stress? Why is it normal? Because the cable's getting pulled in this direction, right? It's not getting pulled in this direction. That's shear. It's normal. So that's what's going to happen to the cable. So it's like, does that help somehow?
Yeah. You can plug in the maximum for the stress, and you have the area, and then just rewrite it to find the normal force of it. And it gives it normal force, the max, and that's the equivalent to the force on the VC cable.
don't have to just square the numbers. What's the diameter?
Yeah, 0.25 inches.
And the cable is 0.25 inches. And so we said before, when that's a diameter, this is kind of a nice way to write it. Pi over 4 times diameter squared, or pi times radius squared. You're more than welcome to take 0.25, divide by 2, and square that answer. But dividing by 2, 2 squared is 4. So that's the advantage of this. And so that's kind of interesting. I kind of find myself looking at that thinking, oh, I could have done that from the start. I didn't even think about that. Should I have done it from the start? My thought is no, just do stuff. Do not stare at this like somehow you're supposed to know what to do. Just get some equations, just go figure out stuff that you know.
That normal force would be the force on BC, correct?
That's exactly right.
And then you
So what I called N here is actually the same as BC. That's exactly right. So in a sense, my labeling system wasn't all that great. Maybe if I had started with this green one, then I would have just, instead of calling that force of BC, I might have just stuck N in there, so to speak. But the point is, yeah, this is going to allow me to solve this. And so if I solve that, I get that N there is 1178. Again, you will not see this kind of in the back of the book, so to speak. They would call that 1.18 kips or something, but I always find myself, as I've told you, wanting to convert that to pounds so that I can just watch the units working. I can see the pounds and square inches on both sides. This feels good to me. And so, yeah, that's exactly right. This really is that force right there.
So how do you know that's FBC and not the?
Well, it's kind of both. In other words, here's the weird part, because it's kind of like, if I call this force of BC up here, and over here I called it W, if those are both the same cable, then they're not both the same, but I got to make sure neither of them goes over the size they're supposed to go over. Does that make sense?
Well, when you said that B isn't a pulley, because if it was a pulley, then they would both
They
be.
would both be.
That's exactly right. And that's what I did wrong at first. I thought it was a pulley and I thought they were identical,
Are they not?
but they're not.
Oh, so this is just a separate cable.
So they're
That's why
totally
it's this
separate.
way
So I mean,
over.
they're the same type of cable, but they're basically tied.
I get it. This is a winch. holding
And it
the
makes
piece.
sense actually, because if it went smoothly over it, that bar would just go hunk and fall to the ground because there's nothing holding it in the position it's in. So, but again, I got that wrong. I just assumed because it was circular, it was. So again, I'm trying to model like floundering around with this a little bit. Like I'm just figuring stuff out. So notice I had right here an equation with two unknowns, but now I suddenly realize this is the same as that. So if I divide 1178 by the cosine of 30, then I actually get. Actually, do this. I think you might have my calculator. Do you have mine, or is that? I had mine out earlier, and now I don't have it. So you might have it. Do you have mine? Nope, I have it. Kidding. 1360. Okay.
I wrote a difference,
I think.
I rewrote a difference.
1360.
Okay. And then of course, if I know f of a b is 1360, then I can put 1360 back in up there. So times the sine of 30, and I got 680. Notice in my case, if you will, I got lucky because I didn't work in kips. And when I got all finished with this, the answer I got was actually not in kips. You wouldn't call that 0.68 kips. You just say it's 680 pounds. So in a sense, I got lucky as a result of this. So how else did we get lucky?
I did all day shift, so I think I'm gonna go back then.
Which is fine. There's nothing wrong with that.
That's longer.
Yeah. And there's nothing wrong with leaving it that way. Call it 0.68 kips. Who cares? So notice we used the 24,000 down here, and we got that cable on the top was 1,178 pounds. So it's like, how come those two Well, first of all, these two aren't the same. That's because they're sort of doing different jobs. So in a sense, if I had just started with this one right here and found its weight, I would have got a way higher weight. But then when I hung it, this cable would have broke. Does that make sense? Because this number is higher than that number. So in a sense, I got kind of lucky. So the right answer is 680. This cable, if I go over 680, then it's basically this cable up here that's going to break. Does that make sense?
The top cable.
Yeah, this top cable is the one that's going to break. So if I put 1,000 on this, my first thought might be, oh, no problem. I can hold 1,000 pounds because look, it's 24,000. Now that's pounds versus pounds per square inch. That's why this formula's got to be used. But my first thought was like, oh, okay, no problem. But then it was this one that broke because it's actually got more force on it based on these two numbers. This is, close to double what that one is, double as much force, thanks to the kind of the way that whole thing is set up.
So is that 680? That's the weight of the box. That's the weight of
Yeah.
the weight you can pick up.
Yeah. And notice that's actually stuck at 30 degrees,
Right.
which is also kind of weird because there's a winch there as though you want to move that to other angles. And so,
Right. Out of curiosity, I don't want to go into like tangent on it, but like if you went to like 25 degrees or 20 degrees, is that going to lessen the strain?
it's going to make it worse on that top BC cable.
It is.
Mhm.
So if you go down to like 50 degrees, it's going to make it to lessen the strain. You can pick it
Yeah,
more.
that's right. Because it's kind of like this, if this thing is really heavy and it's down on the ground, I don't want to go to it. Oh, pick it up now. That's really, you're super weak. You can lift like 10 pounds like this. Whereas if you're down here and you lift it straight up, so that all your force is with it, you can lift a lot more.
Right. Okay, that makes sense.
And by using the maximum.
So it's
you
saying
find the
that
maximum weight.
30 degrees, it could only allow 24 SKI, but that 30 degrees or 24 is going to change as the angle changes.
No, the 24 won't, because that's how strong the cable is. But the weight, the 680 that we got for the maximum weight load on it,
So we should find a maximum 90 and then maximum 0.
yeah. So as an engineer, either that would be stuck at 30. And notice the way it's drawn, it's like meant to pivot. It's not like it's welded in that position. But if you were an engineer, you'd have to make a chart that says at 30 degrees, this is your max. At 40 degrees, this is your max, and something of that nature.
That'd be simple enough.
Yeah, it wouldn't be hard. Redo it with a bunch of different angles and get different weights. So do you see really what happened was we were basically given this number as a limitation, and then we worked backwards to find, what's that normal force. So it's not a different equation. So when you see the phrase sigma allowable, just think, oh yeah, in the past we just figured out what that was. And in the past we figured out what that was, and then we would go to a chart to choose the right pipe that had the right PSI number to produce that. Now they're saying, oh, it's already built and this is already what's on it. So then you work backwards and figure out what the normal force is that you can kind of put down for a maximum.
I just don't think I would have never really known where to put that normal stress.
Yeah, and then in a sense, that's why I drew that picture earlier, because I drew that cylinder earlier to help you understand that it's like that's the direction normal is going, and that doesn't have to be a metal cylinder. It can be a piece of cable, a piece of string. So it's the force that's basically in that direction that you're talking about. Okay, we got time for maybe one more. So again, just some similar weird contraption that some person set up. Do you see, without even reading this question, do you see that it's the same question? Why is it the same question? Well, they didn't tell me how much force is hanging there. They said it's P for pounds, I guess. I don't know. So here's this weird contraption. It's got some force pulling down on it. And notice we are told an allowable stress. And then wait a second, I was wrong. They did tell us what P is. It's 20 kilonewtons. So don't we know the force and the allowable? It's like, what are they asking us for then?
They're asking if it's going to fail or not.
I'll read it. They're saying choose the right diameter size. Like, in other words, you know how strong it is. If this is a certain kind of steel, it's all the same PSI strength, but it's like, well, what diameter of it do you need? Does it make sense if it's too small? It snaps apart. But if it's a lot bigger, it's not going to snap apart. So this is the same thing. Last time we knew what size it was, and they said, tell us what the load is. This time we know the load, and then we got to choose the diameter of the material. So-
we're missing the A instead of the-
Exactly. Yeah. So we have sigma, we have n, we just don't have a. So it's no different. It's just an algebra equation.
When it's talking about diameter, it's talking about the pins on C and D, right?
No, because they're talking about, and your question is really good. They're saying it's about these aluminum rods. And so it's the rod itself. Now, is there a pin at those connections that's maybe way smaller that could shear off, by the way? And is that a problem for the next section? Uh-huh. Or is that something, we could even do in this section? But those pins could shear off. That's exactly right. Well, let's not be lazy this time. I'm going to draw a free body diagram this time just because I think it's interesting. And I see that I've got this force pulling down, and I've got this going in this direction. So this is point A. Based on our discussion a second ago, do you know what way the arrows are going in those two other, like, are they pushing or pulling? By logic, you should be able to figure it out. Do you agree this has no choice but to go this way toward B? Why does it have no choice but to go that way? Why can't it be like this? Because then they'd both be going down and there's nothing to hold it up. So in the vertical direction, that one had to go up. Otherwise, there'd be nothing to stop that 20 kilonewtons going down. So I know that has to go up. So it's under tension. And so right now, I could write some of the forces in Y, even before I do anything else if I wanted to. I could say I've got force of AB going up. That's why I called it positive, but it's modified by the sine of 45 degrees. So that's the part of it that's actually going up. And then I got 20 kilonewtons going down. Again, I find myself wanting to call that 20,000 newtons, just because maybe I'm going to end up in pascals and those are newtons per square meter. So maybe that's a waste of time. And so, hey, I like this equation, I say, because unlike last time, actually, no, there's only one thing I don't know there. So I can actually find the force of AB right now. 20 divided by the sine of 45 is 28. So force of AB is 28,284.3 newtons. And I'm just going to point out, because it's cool, hey, I also know that's in tension. Not to show off, but I already know that. If I had left 20 as kilonewtons, I would have just got 28.3 for that, and that'd be fine too. But it's sitting there in newtons, already ready for my newtons per square meter in case I need it. So I don't know. That's just kind of my growing philosophy. Okay, cool. Am I done? Do I care? Am I finished? Can I just calculate this? Well, remember, notice they said 2 aluminum rods, and they seem to be implying they're the same exact rod because they told us what's allowable. Well, I guess not necessarily, because that allowable doesn't talk about dimension. But we're assuming they're both the same. So can I just make my calculation off of this? Well, I might be able to keep that one from breaking, AB, but what if this force causes the other one to break? So it's like, I need to know how much force is on that one too. So back to my free body diagram. Do I know what's happening over there to AC?
Yeah.
I do. Since B pulled it right, then AC has no choice but to pull it left, which means it's also in tension. So the sum of the forces in X would be, well, I have that 20 isn't doing anything in X, and so it's left out of the problem, but I have force of AB going right, which is, I'm going to go ahead and just write it in here, 28,284.3 going well, at the angle it's at, but I got to modify it by the cosine of 45 so that it's actually right. So that goes right. And then force of AC just goes left. I don't have to modify it at all because it's aiming straight left. So that's kind of cool. So force of AC also in tension comes out. Is that a coincidence? 20,000 newtons also in tension. Does anybody know? Is that a coincidence? Actually, it's not. I just want to know if you can figure out why.
Yeah, I figured it out. Wait for it to set it.
Take a look over here. If this thing is pulling this way, would you agree that's its X? And this is its Y? Well, didn't its Y have to be 20K to match this 20K? But since this is a 45-45 triangle, then wouldn't this one also have to be the same? Because it's 45-45-90, so those two sides are going to be the same. So that's actually not a coincidence. Kind of neat. Oh, so that's interesting. I find myself just stopping to think, oh, force of AC has less force on it. Force of AB is getting the worst of it. You see what I'm saying? Like it's working harder. It's working, what is that? 8,000, like 30% harder, something like that. 40% harder. It's getting worked a little bit more.
Just because it's sustaining most of the line.
Yeah, I think it's because it's kind of having to do X and Y work, whereas the AC one only had to do X work. So it's kind of like it had to exist in both dimensions. So again, I've got this kind of nifty sigma equation. Sigma, I don't really need to write allowable in there. I'm just doing it because it's fun, but I've got this equation right here. But the problem is those are both those are normal forces. Do you understand these are both normal forces? Do you understand? Stop and think about that because I don't think that's obvious. And we have to distinguish a lot in this class. And I'm finding myself very confused in later chapters trying to keep all this straight in my head. But is the cable being pulled on normally? Yeah, that's why it's a normal force. It's not being pulled this way, it's being pulled this way. So those are normal forces. So that's why there's an N up there. So those are both. So what do the question is, what do I put in there? Like I see, oh, they told me allowable is 150 megapascals. What am I going to do with that?
I converted it to kilopascal, just to kind of match.
Yeah, so that would be kilopascals. That would be megapascals. So this is the downside of kind of what I tend to find myself doing. Now that I have it to pascals, not megapascals, this is newtons per square meter. So I don't know if that's worth the trouble, but at least that's pascals, fine. And on the other side, I have area down here, and I don't know that, but that's going to allow me to find the diameter in just a minute. But then which one of those do I put up there? Or do I just put them both?
You put the bigger one. Because that's the one that's working harder, so that's the one you have to stick out for. That one's gonna fail.
Well, notice up here what they said right here. They're telling us they're using the same exact material, but they're saying you don't have to order the same diameter. If it's a little smaller and doesn't have to hold as much weight, then just make it smaller. So in this case, they're actually asking for both. They're not the same piece of, so this is not, what's the limiting factor? What's the smallest area I could get away with?
But
Although
the
they could have
client-
asked that. Does that make sense?
The
Because
client said money's no object.
yeah, the client said,
We're gonna use the bigger one.
so actually I've got to do both, I guess. So let's switch this out. Isn't area pi divided by 4 times diameter squared? And notice by default, and this is one of the reasons I do what I do, notice my diameter is going to come out in meters. And because I took the time to write that out, I know that now. So the top is in newtons. I'm going to get a meters for my diameter. So I'm gonna have to put force of AB in here one time, and I'm gonna have to stick the force of AC in there another time. And then just solve for D. So that's good because it's an equation that only has one unknown, kind of a gnarly algebra equation. Of course, if I looked in the back of the book, I'm more likely to see 15 millimeters for this one, right? And 13 millimeters for that one. That's probably what I would see if I looked in the back of the book. Now, as a side note, in the real world, it's oftentimes expensive to say I need one of these and 6 of those and 4 of those and 3 of those. It's actually easier to manufacture things and put them all together if you just say I need all the same size. Like that actually might save you money, might save you more money to just say I need all the same size rather than some smaller ones, in which case, they're having to sort through a bunch of things. So
Get discounts on both.
So of course, if I had to pick one, I would pick the larger of the two, right? Because I got to make sure it's big enough to do the job. The 13 millimeter one is big enough to do the AC's job, which wasn't as hard, but it's not big enough to do AB's job. So if I was, in this case, I'm not choosing the minimum one, I'm actually choosing the maximum one. See how confusing that could be? And like, you certainly wouldn't want to get that wrong. It's kind of cool. So in the interest of time, and also because I really don't think we need to do this, just take a look at this last question that we won't do. What do you notice it's asking? It's the same exact question, actually. Well,
Opposite.
yeah, what do you mean? Say it again.
Gives us the diameters to start.
This time it gives you the diameters and then asks you for the limiting force, kind of like we did earlier. And notice they made AB a little bigger. We already figured out from the last problem, AB should be a little bit bigger. AC could be a little bit smaller. And so they actually kept with that theme. But we got 13 and 15 millimeters and they have 10 and 8 millimeters. And so what's the largest force that can be lifted? And so I would have to pick it this time because I don't have two choices. It's just, I'd calculate both forces separately, kind of like P of AB. And I'd also calculate P of AC. And in this case, I'd be choosing the lesser of those two because I don't want to lift more than I can lift. Last problem, I want to choose the biggest diameter because I want to make sure I have enough strength to do the job. This time, I want to put weight on it. I want to put the least weight of the two weights. So armed with that, I have a feeling you'll be successful with 1.7. Again, I would highly recommend you sort of go home and do 1.7's assignment. There's not that many questions in it. Go do that right away so that start a class. I mean, I talked with Caesar at the start of class about none of the others of you asked me about question 141 and dynamics. You wouldn't have asked me that. But that's a really hard problem. And so, there can be some curveballs in there. If I have time, I try to warn you about that stuff. I don't think there is in this section, but it's always good to, start the next class before we introduce something new and say, hey, I was having trouble with this problem and can we talk about it? You can always email me or text me and say, can we meet in class early? I actually kind of hang around here anyway. There's like a half an hour from between 12:30 and 1 that I hang around here anyway. So even if you didn't ask, I'm sure I'll be around.
Real quick, can you go over the algebra of that last part? I'm getting like this wonky number for, I
Yeah.
have 150 million.
Oh yeah, there is actually something I want to mention about that.
Oh, yeah.
You got to be really careful when you divide by pi over 4. Like you're actually dividing by a fraction. So the best thing to do is get rid of fractions, like take your 150 and just to save a little bit of time, I'll write I'll write 150 mega pascals. And then I would be multiplying times pi over 4 times d squared, and that would be equal to 20K or whatever the other side was. And so here's where you got to be really careful. When you divide pi over 4 to this side, if you type in 20 divided by pi divided by 4, you're wrong. You have to, because really dividing fractions, it's actually 20 times 4 divided by pi, isn't it?
Right.
That's really tricky. I mean, it's something you know from algebra, but
Right.
if you type what that says, unless you put parentheses around that, it's not going to work.
I did put parentheses around it, but I get why that would be.
So basically, you're going to divide by that. You're going to divide by 150. And again, this is kind of why I like to not have mega and kilo here, because I feel like I'm going to screw that up.
Right.
So out of stupidity on my part.
You would just put kilo and then kilo up there, and that way you're all kind of the same.
You could do kilo, but I find myself just wanting to do newtons so I can stare at the units. So even though it's a waste of my time, I have 20,000 and 150 million on mine.
Right. And so if you stayed in the kilo realm, are you getting millimeters? What are you getting?
Yeah, and that's exactly why I put those units on it. So let's stare at this a second. So for me, I'm putting in, and for another shortcut, by the way, 1, 2, 3, 1, 2, 3. If you're dividing those, does it make sense in your head? You can say 4 of those are gone and 4 of those are gone. So I'm really dividing 2 by 1,500 or 15,000, whatever that is. So if you want to save a little time, you could do it there. But in my case, this is newtons and this is newtons per square meter. Pi and 4 are unitless. So when I divide that, I'm getting square meters. So I have d squared equals square meters. So when I square root both sides, I'm getting meters.
I see. Okay. That's gonna take some issues too. Okay.
Yeah, and the good thing is if you screw that up, you get an answer that's like they're not that big, or something's when you divide by 4 when you should have multiplied by 4, you get a gigantically weird answer. So
Well, I was like putting inches squared because I was caught in that other world.
Yep.